Okay, so let's erase this waiting room here. So last time we had just introduced particle swarm optimization. That is one of the more popular optimization meta-heuristics. It's right up there with things like ant colony optimization. And so how did PSO work? And so we mentioned that PSO was inspired by, I'm not going to go through the whole summary here, but basically inspired by flocking behavior. And a lot of models of flocking behavior have basically areas of attraction and repulsion that allow a flock to somehow stay dispersed locally, but globally move together. And so this way you have some form of local exploration, but you together kind of constrain your exploration and you say, we're going to sort of explore as a team. And so nobody wants to be searching in the exact same spot as everyone else, but nobody wants to be searching very, very far away from the group. And so that was kind of the motivation behind this. And the claim was that for things like artificial neural networks and so on, the space of the weights, the parameters that you were searching over were such that it may not make sense to search over a huge group of these, because you might end up finding a lot of very distinct solutions that have very similar fitness or very similar performance. And if you spent all of your time comparing across these very different solutions, you might waste a lot of time where you could just be kind of exploiting locally. And then once you've kind of exploited locally, then you can try to move away and find new areas. So it's kind of a depth first search instead of a breadth first search in this kind of meta-heuristic space. And so the way this algorithm looked like is you basically initialize a random set of positions and velocities where the positions are your candidate solutions. And so from that point, you can then evaluate the performance of each candidate. And then that allows you to set up and maintain a so-called personal best or p-best, which for each particle is the best position and performance over the particle's individual history. And then globally, you looking down on the system can set up a global best or I guess you'd call it a G-best. And this is the best position and performance across all particles and their histories. And so it's the p-best that really is the output of this algorithm. or I'm sorry, the G best that is really the output of this algorithm. And so you keep updating the G best, which is kind of the best that we have found so far. And so what then does the movement look like? Well, then the movement is basically you're going to have these particles that are going to be attracted to their personal best, and they're also going to be attracted to their global best. But the level of attraction to these two things are going to be random variables, and this is going to create some sort of stochastic motion in velocity space. And then they'll have an inertia, which will then further move them along. And so even though the attraction to their personal best and the global best is affecting their velocity because they have inertia, even if they radically change their velocity, they might still keep moving in the same direction they were moving in. And so that ends up giving you this exploration feel. And so the way those dynamics look like, and I'm going to flip to the next page here, is that on each particle, then you've got some velocity vi at the next time step that is going to be equal to the velocity at the previous time step, plus some acceleration hyperparameter. So I'll call this acceleration. And then that gets multiplied by this input, which I'll have a random variable RP. So this is a random variable that is uniformly distributed between 0 and 1. And then that is multiplied by the difference between the particle's personal best and the particle's current position. And then I've got another random variable that I add in RG. So I'll also mention that this is a separate U01 that is got the global best minus the individual's current position. And that whole term there is basically scaling that acceleration. So you can kind of view the acceleration as some sort of learning parameter or step size as you wish. And then that learning parameter or step size gets scaled by the difference between the current position and the personal and global bests. And then those individual differences get scaled by random numbers between 0 and 1. So the alternative form that you see of this, so alternatively, this is often implemented slightly differently, where you've got the next position or the next velocity is equal to the previous velocity times some inertia. And then that gets, you then directly add in everything that's above here. So this whole term gets placed in right here. And so in this perspective, this W is an inertia, and it works very much like the acceleration. In the last slide, we talked about historical best. So I guess, I'm reading a question here. So in the last slide, you talked about the historical best. So I guess we need to do a bookkeeping of such things. Yes, so these, if I were to highlight these things, this personal best and this global best, these two variables that I've just highlighted on this screen, you can think of as having to keep track of these variables as well as the positions in which so these are the positions in which they occurred. So you have to keep track of these positions as well as the value of the function at those points. And so that is, every individual has to have memory of where it saw its personal best and what its personal best was. And then the whole system has to have memory of where it saw the global best and where that global best was. Now, if you're willing to do that search, the global best should be included in all of the personal bests. So whether you want to, depending on how many particles you have, maybe you don't need that extra little bit of memory, but it's not that much extra spatial complexity to keep track of the global best. But yes, you do need bookkeeping to keep track of all those things as these particles are swimming around. Yep. All right. And then from there, we just update, once we've calculated our velocity, we have to update our position. So then I'll go back to this darker blue, update position. And because we're not simulating, oh, and I see another question here. Will there be a tendency for one particle to always be the global best? Well, it's not that there's, of course, the global best has to be discovered by a particle, but then the particles can stray from that global best. And so there's nothing that is guarantees that a particle is going to be close to the global best, or even all of them will be near the global best. It's just saying that the global best puts out an attractive field, and every particle, as they make their motions, feel a nudge to come back to the global best. And so the idea here is that you're constantly trying to be sucked back to the global best as you're trying to, you feel like another sort of sucking force being sucked back to your personal best. And these two things are in conflict, and there's a little bit of randomness. And then you've got your inertia, which restricts how quickly you can turn. And all of these things together hopefully allow you to discover new candidates that you have never seen, and maybe the whole group has never seen. And then that will gradually shift the global best. And then that will move the group around. Because if you now discover a new global best, then now gradually the group will then be attracted to that new global best. And so there is communication through the shared global best. When we say that we are recording the global best, that actually means best seen so far across all candidates. That's correct. The global best is, our algorithm has to keep track of that. And then I see is x to the p and x to the g position or velocity. Those are positions. Whenever I say x in this framework, x is position and v is velocity. So I'm using the differences in position to drive new velocities. All right, so then when we update our position, then that ends up taking a pretty simple form where we just say that the position is the previous position plus this velocity. And I can say, I guess I'll do ti plus 1. So so physically, you normally would expect to see some coefficients in here. So, in physics, we would expect to see coefficients, translating from velocity into position. So, for example, we might expect to see some delta t time. But we are sort of assuming that this delta t is equal to 1 here. There's one way to view it. Or we're sort of assuming that we can play with a time scale by playing with these other terms up here, the inertia and acceleration. So basically, if we added a bunch of extra hyperparameters into this position update, we just create a bunch of degenerate dynamics. And so it would be these things where if I increase my inertia and then decrease my time scale, that ends up being equivalent to increasing my time scale and decreasing my inertia, and so on and so forth. And so just to reduce the degrees of freedom of the hyperparameters, then they just make the position update really, really simple, and then make us focus on just inertia or just acceleration. And that's it. So that is the basic particle swarm optimization. And so today I want to then explore a couple of different minor variations of PSO, and then push forward into where we're going to go next in this next. I don't know if I've made it a separate unit or a separate set of lectures. I need to go back and look, but just in general where we're moving next. So before I move on, are there any questions about the basic operation? And I guess I should add, to close the loop here, is that we loop back to function evaluation and repeat. And then that drives the swarm around and hopefully finds things. So are there any questions about PSO, about this general framework here? Okay, I don't see. Oh, I see a hand up still, and maybe, I'm sorry that I missed that earlier, but I think Swastik, you probably asked the question, so I think I probably just missed that hand. So I'm gonna hit clear. Any other questions? Okay. All right, so that's the basic. Okay, what if we have multiple best. So there's only, we define best in a unique way here. And so I guess there's sort of a rare chance that you could have two positions that tie. But if there's a tiebreaker, we just don't really worry about the new one. But we're sweeping over continuous spaces in this algorithm, generally speaking. And so we usually don't worry about the tie-breaking case. And so there's just a unique best. So as you're swimming through this, then it's like a ratchet. And so you keep getting better and better and better until eventually you don't have to update that global best anymore. Okay. Does PSO work for multi-objective? John, that's an excellent question. I am not going to cover multi-objective PSO, but not surprisingly, there is actually a couple different multi-objective PSOs. And that would be an interesting final project example, for example, is you want to say, I want to study multi-objective PSO and compare it to multi-objective genetic algorithms, for example. So I think if I don't have an article already in this unit about multi-objective PSO, maybe I'll drop one in there since we spent so much time on multi-objective. But if you were to Google for multi-objective PSO, I think the article that I have right in front of me that references multi-objective PSO comes from 2006. So around 2006, 2008, I think you start seeing people implementing multi-objective PSO. All right, any other questions before we jump to variations on this theme? All right. So now we're going to introduce these so-called at least I call them L-best versions of PSO. And so far we've been talking about particle swarm optimization, where every individual has its own P-best, and then the group has a global best. But you could also imagine a more narrowly constrained PSO where you only can see a certain number of individuals. And so that your kind of global best comes from your narrow perspective of the world. And so, so you can now introduce PSOs with these kind of topological constraints. And so we are going to introduce the notion of a neighborhood inside PSO. So imagine we have a neighborhood of size n, and we're going to place all of our agents on a communication ring. So in this sort of simplest case, we imagine we have, I don't know, these number of agents, we'll say S agents, and they are all connected so that agent 1 can communicate with, well, I guess I'll make these non-directed links. Agent 1 can communicate with agent 2 and agent S. Agent 2 can communicate with 3, and so on. And then, S can communicate with 1 and S minus 1, and so on. And so we've got this ring topology. And this is just a communication. So a communication topology. So I want to make it clear this is static in this version at least. So it is not like as these things are moving around that they are only communicating with ones that are nearby them. We're sort of saying that regardless of where they are in parameter space, 1 only can talk to 2 and S, 2 can only talk to 1 and 3, and so on. And so it's physically speaking, it's a little funny to justify that you can only speak to a small neighborhood, but that the definition of that neighborhood is fixed as if you're flying in formation. Although when you're flying, you're definitely not flying in formation. So, but that's what we're going to go with, at least for this version. And so then now we can go back to this neighborhood size n, and we get to then define how many agents get to communicate here. And so the idea here is that this neighborhood that I'm drawing would correspond to a neighborhood size of 2, whereas maybe if I were to go out farther, then this corresponds to a neighborhood size of 4, and so on. And so the idea here is that, so using one agent as a focal agent, maybe that's a bad, maybe I'll use the highlighter for that. So if for every agent that I focus on, then this is a hyperparameter, this neighborhood size. And I'm saying that every agent can only see that number of agents around it. And so if I increase n to the point where it's s, or I guess s minus 1, then every agent can see every other agent. And so these windows float around every agent. And so I'm focusing on agent 1 right now, but you could imagine I flip this and I could focus on agent 2 and so on and so forth. And so the idea here is that I can now calculate a local best for only the current neighborhood. And so this particular neighborhood here has its own local best. And so does this neighborhood here has its own local best. And so everyone, basically the local best inside the neighborhood is sort of like the best personal best for all of the agents inside that neighborhood. And then, so in the simplest versions of these PSOs that have these neighborhoods, you then can replace the global best with the local best. And so now, instead of paying attention to the best that everyone's seen, I am only paying attention to the best that my local neighbors have seen. So I'm going to switch back temporarily. So in the formula here, this xg that's up here in the top right, imagine that to be like an x superscript L, where that's just the local neighborhood in my neighborhood from my topology. So with that in mind, let's try to get a little bit of interaction here. And so what do you think the result of that would be? So how will this affect, I'll call the optimization performance of PSO? Does anybody have any ideas? I'll let some of the ideas come in and then kind of summarize them here. All right, I see some ideas coming in about speed, about diversity. All right, so for those of you who are saying things like more diversity, less accurate, then I assume you're talking about the local one is going to be this way. So relative to the global one, how is the local one going to be better or worse? So just to summarize here, just to read things out loud, I see things like this ensures more exploration than the previous approach. I see greater exploration of the parameter space since they're not all drawn to a single global optimum. I see faster, more diversity. So diversity to me sounds like another exploration case here. Instead of one definite solution, we have multiple candidate solutions. Less accurate. So less accurate is interesting because that kind of relates to me. Maybe there's these trade-offs here. Suboptimal, more time to converge. So that sounds like slower, more time to converge. As a clarification, are we finding the local best for the neighborhood instead of each agent, or calculating the global best for the neighborhood instead of all the agents? We are, instead of calculating the global best, we are calculating the local best. So we, as designers running the algorithm, might keep track of gbest, but the agents themselves are going to be attracted to the local best inside their local neighborhood. They are not going to be attracted to the global best. I see requires more storage. That's true. There's more spatial complexity we have to worry about here. I see can it take more time? I see faster to update each step, but slower to converge to global optima. I think that's probably the case um, if you are having to recalculate these locals all the time. And so so in general, I'm seeing that there are computational, so some people are bringing up that there are computational consequences to this. And I think that is good to point out. So if I were to put up, computational, or I'll say complexity changes, well, we can see that there is more storage, you could say, needed, or spatial complexity. We need more memory, so that you can think about this, more memory is needed. And there might be more computational complexity to calculate all of these things, but that would probably take us to go into a more detailed analysis, because maybe somehow it's cheaper to calculate all these local ones, or maybe calculating all the local ones separately won't be that much worse than calculating one big global one. But then there are the kind of optimization characteristics. And so I see these harder to climb out of local minima, things like that. And so from an optimization perspective, I see a lot of things about exploration, and I like that. So I'm going to write that down, more exploration. And so the idea here is, since they're attracted to different points, then they're naturally going to be exploring differently. And so if there's more exploration, then we might think that we are going to get more accuracy. In other words, we will get less trapped in local optima. And so, and yeah, I see less exploitation. And so there's, if you want to be in that local optima, you might not exploit it so much. But if you're worried about getting stuck in a local optima, then you then can pop out of it. So I see one advantage is that one group that hits a local optima, we have other groups can still explore their areas. That's right. So that's kind of the motivation for this, is like, how do you prevent the swarm from getting stuck in a local optima? But then the downside of all this is that you tend to be slower. So I'll maybe on the, so I'm trying to figure out where I should write this here, but then I'll maybe write that this is slower. So you get slower to convergence, even though, which kind of makes sense. So we are increasing exploration. So the particles are spending more time exploring, less time exploiting. So they're slower to converge. But the upside of that is they're less likely to get trapped in a local optima. So that's kind of what they added by this local best parameter. And so what's nice about that is, because we have control over this hyperparameter n, which is the neighborhood size up here, then we have a way to kind of dial in more exploitation, less exploration, and vice versa. So if we are more concerned about speed, then we can make the neighborhood size very large. And by doing that, we basically turn the local best option back into the traditional global best option. But if we are more worried about getting stuck in these traps, then we can reduce the neighborhood size, and then that provides us a mechanism for the flock to be more spread out and hopefully exploring a wider space. And you can imagine that, in the extreme case, if you make your neighborhood size 0, then you basically stop paying attention to any social information. And that's kind of this extreme where you don't get socially stuck, but you also don't have any of the benefits of that sociality. All right, so I see here, how are we exploring okay, just got it. All right, so it sounds like there's a question here, but that's been resolved. Great. All right, so any questions about this local best idea here? Could I add a hierarchy of neighborhood and include the G best of a particular neighborhood So there have been versions of particle swarm optimization that uh, do things like always keep a global best and always have a personal best, but then also have this local best. And so you've got these three attraction points that are pulling every individual around. And as I was about to mention, you can also play with the topologies here. And so you don't have to have a ring topology. You could have a variety of topologies. And those different topologies are going to have different effects on the dynamics of these optimization things. And you can definitely do all of that. So does that answer the question there? So I'm just sort of presenting some of the basic versions of PSO. You could definitely further vary them, but I just want to sort of give you an idea of the dimensions on which you vary them, and then you can go out and find in the literature the ways in which people have done those variations. All right. So yeah, so I'm just making sure I'm covering everything that I wanted to mention here. That the optimization network size, the neighborhood size, that's one of our big parameters. And the topology is definitely something else that we can play with. So we don't always have to have this ring. Okay. All right, so now so have to think about some the problems that we get with particle swarm optimization. So that's the basic on how we affect the communication. If we go back to thinking about these update rules, one problem that people have noticed here is that if we look at the velocity, then this velocity parameter has no bounds. And so in principle, you could end up, these particles could, even though they start slow, then they end up possibly being able to explode to the point where they just have so much, especially if they have a lot of inertia, then their velocity might just keep building and building. You might slow them down, but then they end up getting attracted to something else, and or the velocity just becomes so strong that you can't end up steering them back. And so how do we deal with this velocity issue? And so there are varieties of PSO that are all kind of framed around this idea of this velocity, of how to control this velocity explosion. I see a quick question here. Apart from ring topology, any other topology would just create silos in the swarm that would be equivalent to having multiple swarms in the absence of ring topology. What other topology can have the same effect of maintaining the swarm by still giving exploration? So that is, you could definitely, so I think the criticism could be that if we're not careful, you could create a topology that creates a group of like a clique, multiple cliques that all talk to each other that are sort of like independent PSOs that don't ever share information. And you might want to avoid that. But it's kind of like in the case where we had distributed genetic algorithms, you can, sometimes there's a benefit to actually having exploration go, to have algorithms running almost nearly in parallel with only minor communication between those little demes that are sort of running off on their own. And so it's non-trivial to say what topology is going to be best. And so people have experimented with a number of different topologies. So you could imagine small world networks and random graphs. And so you could even adjust the topology as you go. So maybe if one particle is tending to always be in a good area, then maybe that becomes more influential and it gains more links over time or something along those lines. So there's the sky is the limit on how you can play with this topology, because it just has it's so flexible. There are so many different degrees of freedom. So I can't say for certain that that the ring topology is always going to be better. There's certainly like a fully connected network that would be another one that that doesn't create these silos for sure. But there's definitely a lot in between a ring and a fully connected. So I would say that having this property of kind of recurrency, where you need a path, you need to make sure that there's at least some way for influence from one to get to another, is probably an important thing to have. So having one single connected component is probably important. But after that, I think you have a lot of flexibility. And I don't want to get too much in detail of that, because again, a lot of literature has been written about this point. But so just imagine different ways in which you could perturb these topologies. All right, so some of the early problems with PSO had to do with things like unbounded velocity. And so, in a bird, then you don't have to really worry about this because there are upper limits to what birds can do. But when they started to simulate these flocks, then they noticed it was pretty clear that as you started to simulate these things, even though there might be a group that were staying clustered together, if some of those individuals got enough velocity, they could go flinging away from the group, and it'd be very difficult to pull them back away and back toward the group. And so and part of the, and so you can imagine a bunch of different ways that you could try to constrain velocity. So, one way is to simply bound velocity. So you could make it so that your velocity update rule tops out, it maxes out. So you could say, we're gonna, max out velocity. The downside of any sort of constraint like that is that at the point where you hit your maximum velocity, you kind of lose feedback. So if I were to go back to that velocity update rule, then across the top here, this velocity here, then if the velocity is sitting at its saturated value, then the problem is that suddenly all of the information, the feedback that I was getting, just goes away. And so maybe there are other ways in which we can try to control the velocity. And so you can imagine, updating that rule to make it so that, maybe there are nonlinear attraction forces. So, for example, if I go back here, and I'll go back to that, you see here, I'm just saying here that the difference in positions drives the next velocity here. But if I were to make weight these positions so that positions farther away got more weight, so like if I were to put like a square up here, or a square right here, or generally another exponent here, then I start getting these distance effects where, as if the group gets very far away from each other, then it would have a huge attraction to come back together. Now, that doesn't mean that they won't build up a lot of velocity and then come away from each other again. And so that doesn't necessarily solve it, but that at least helps maybe constrain, cohesion. So there are a bunch of different things you could do to these dynamics to try to solve this problem of unbounded velocity and these far out groups. So, and then another thing you can do, which kind of relates to kind of blends these two together, is, well, rather than focusing on the distance or focusing on bounding the velocity, then why don't I have an adaptive acceleration, which is kind of like an adaptive step size. And I see a comment here, birds will also slow down and change directions. Right, and these particles can change direction. So a particle that suddenly feels a strong attraction force on its back will come back around. And I guess the point here is that the birds can kind of sense when they're farther apart, and then will maybe turn around and come back. Whereas these particles might get taken over by their inertia, and or if they have a high velocity, it might take a while for their velocity to unwind. And so that goes along with my nonlinear thing, is that if you added squared terms to those positions, then once you start straying from the flock, then very quickly you feel an urge to rapidly whip around and come back around. So a simpler implementation to these things is just to have an adaptive acceleration. And so this is, again, kind of like an adaptive learning rate or step size. And I'll just remind us on A. So if I were to go back and look at this, this acceleration here, then this idea here is that right now this is a constant parameter here, but you could imagine that across different regions of space or through different histories, then this acceleration might get smaller and might get larger, and maybe actually across different velocities. Then, you know, as your velocity gets higher, then maybe you crank down this acceleration component. How squaring will help them attract? As understanding should increase the velocity and hence increase the problem of unboundedness. Well, so the thought was here is that if you notice this here is a difference, so this term that I'm kind of highlighting here with this laser, which I hope is coming through, is trying to show here that the position of the individual, how different is it from the position of the global best? And so if this individual gets very, very far away from the global best, then this becomes a large distance. If I square this, the distance becomes even larger. And so the thought is that if I have a large velocity moving me farther away, then maybe by squaring this distance, that I will then get an attraction that will come back. And maybe I need to actually add, maybe, I'm oversimplifying by saying I'm squaring it here. Maybe I need to do something a little more sophisticated that makes sure I keep the sign of the difference in there, so that if I get far away, if I'm moving far away, then this will create a stronger and stronger force to move me back toward the global position. And that's kind of what I'm just trying to say here. But it was just kind of a motivation for this idea of an adaptive acceleration, because instead of modifying the way I'm perceiving distance out here, instead I can dump that all into this acceleration here. So if my velocity has gotten a little too large, or I'm getting a little too far away, then maybe I can adjust this acceleration instead. So those are, I mean, primarily these two, this bounded velocity and adaptive acceleration, are the primary ways that people use to deal with this early problem of unbounded velocity. Then once you have that, so simple squaring will just increase velocity and may not bring it back, continue to preserve the sign as well. Yes, that's again what I'm saying, is that you can come up with a more intelligent way to maintain this sign, as opposed to just squaring the velocity. But there's the basic idea is I want to make it so that as I get farther away, the restorative force becomes greater, which we can potentially implement with this adaptive acceleration. So although bounded velocity seems like the most straightforward way, the downside is it cuts off feedback. I could say, but this removes social feedback. And so maybe an adaptive acceleration is nice because it's a way for me to keep my social feedback, but then kind of still change the way in which I'm adapting my velocity so that I have the feedback, but I don't have a rapid acceleration of velocity too large. All right, so that's how to deal with the unbounded velocity. And then the other variations that, as I mentioned before, are these alternative topologies. And there are many, and it's very complex to say how one topology is going to affect the others. But that's basically brings you to the state of the art in kind of a modern PSO. And so, for example, if you were to go into MATLAB, it's just easy for me to bring up and type help particle swarm. So like, MATLAB has their own particle swarm already pre-written. Then this particle swarm algorithm, they basically give you the steps of their algorithm, and it is implemented in a very similar way that I've kind of mentioned here. And so they have, for example, a neighborhood size. That neighborhood size can actually adapt over time as well. And so this is another example in the kind of state of the art, is that this here can be adaptive based on swarm performance. So you can tell MATLAB to start with a particular neighborhood size, but then MATLAB has rules that then, based on how frequently the global best has changed, it can then change this neighborhood size. MATLAB also has an inertial parameter. So they have an inertia. And then that too is adaptive based on the swarm performance. And so by swarm performance here, then this responds to how often gbest is updated. And then otherwise, it operates very similar to the algorithm that I've outlined to you there. They've got an inertia instead of an acceleration parameter. They have a p-best and a global best, and that global best is determined by this neighborhood size. But they allow their neighborhood size to change dynamically over the execution of the algorithm, and they allow the inertia to change dynamically over the execution of the algorithm. The schedules in which how these things change with respect to this global best down here is complex, and there's a bunch of different ways in the literature that people suggest how to do that, and the MathWorks people have chosen one of them. I won't go into detail about that, but I just hope you can kind of see, along with adaptive acceleration, how you can also adapt neighborhood size and inertia to control velocity and also hopefully control exploration and exploitation on the fly. And that's basically the basics of the state-of-the-art particle swarm optimization. I want to take the last couple of minutes of class here, the last little bit of time here in class, to describe more exotic versions of particle swarm, and then where we'll end up going from here as we'll move away from optimization and more towards consensus for a little while, as we start talking about things like opinion dynamics and how they relate to this swarm intelligence. So any questions about this basic particle swarm optimization? Okay. All right. So not long after particle swarm was introduced, and so particle swarm optimization, I think, is attributed primarily to somebody named Kennedy. So Kennedy et al. Are kind of PSO founders, and then shortly after they released PSO, they came up with a radically different version. So the same group suggested this other one that I'm going to write here. I'll write out in a second, but the fully integrated particle swarm. Now, as a quick aside, so I think at least one group is doing like shuffled frog leaping algorithm. So the SFLA, shuffled frog leaping algorithm, is another one of these algorithms that was greatly inspired by particle swarm optimization. So PSO and the basic idea of PSO has inspired a number of other approaches. So you can see a lot of inbreeding among these meta-heuristics, which ends up becoming complicated because a lot of times you end up finding meta-heuristics which end up reinventing other meta-heuristics. And a lot of these meta-heuristics can be reconceptualized in terms of things like genetic algorithms and so on. So that is something that it's just interesting to study from a kind of a meta level by looking down on this. And this group itself came up with this fully integrated particle swarm that they intended to be higher in performance than particle swarm, although, and this is back in 2004. So obviously has not caught on, and I think it's probably because of the complexity of the hyperparameters involved in fully integrated particle swarm. Although it potentially had the promise to maybe be I don't know, a better optimizer than PSO. And so the basic idea behind fully integrated particle swarm, which itself was actually a response to other people's response to particle swarm optimization. So there's a whole bunch of particle swarm variants out there. And this was the original author's response to some of the responses. And so their thought was, what if we update the update rules a little bit here? And we say that the velocity is going to be equal to, and they just put a general inertia parameter in front of this whole big update rule. So, and it's the previous velocity plus, and then this is an average, 1 over ki, where ki is the size of the neighborhood around agent I. So then I am going to then sum up all of the neighbors times some, I'll call this, I'll just write, maybe I'll put it in a different color to make it clear. This is a random variable between 0 and some upper bound, I'll call phi. And all right. And so just to make it clear here, this is random number between 0 and this parameter phi. And then this here, you can view as a average of the p best from every individual in the neighborhood. And then this here is the position of agent I. And then we've got our standard position update rule. And so this fully integrated particle swarm, M is where M is the, oh, I guess I put M there, but I should have, so maybe I'll erase. I want to be careful here because I wrote, this is another one of those cases where I have in my notes this subscript M, and I want to make sure that I don't correct the wrong thing here. Actually, I probably can bring up, so the FIPS paper I actually have, I think I shared online. If I think it's already on the web page. And so I'm looking over the FIPS paper now to make sure that I didn't, that I don't upset anything. Velocity of I, why do I have this? Sum. Well, for now, I am going to, I'm just trying to communicate the basic idea behind FIPS. And so I think when I originally took these notes, I originally was going to write this average in, and then I decided to just break it out into PN. And so I am going to cross out this sum. And instead, the basic idea is that I am taking an average here across all of the individuals in my local neighborhood and their p bests. And so I have a way in which I am my p, and then I'll call this, I wrote that pn, but I think this really was supposed to be pm. And this PM is supposed to be a weighted average of the P bests of everyone in my neighborhood. And so it's fully informed in that I have defined a neighborhood, and I'm not just interested in the best value across the neighborhood. I'm interested in everyone's best value, and I'm pooling all those best values together into one kind of weighted P best. So it's like an aggregated best value, and that is the value that I'm going to be driven around to. And so it's this way of integrating all of these P bests together at once, rather than just effectively taking a single P best. And so this fully informed particle swarm, its idea was that rather than trusting a single best, like if everybody has the same single best, then we basically treat that as a global best and we just get attracted to it. But if there are multiple P bests out there, then we shouldn't just be attracted to one of them. We should be attracted to some centroid of those, because there might be even better ones there. And if we all go there, if our P bests gradually start to reach consensus, then we might come to consensus on the global one. And then if we all agree on the P best, then maybe we'll all stay there. But if one of us disagrees, then it provides more sort of space for us to move around. And so it's this idea of aggregating P bests rather than picking just one. So I guess I could write that down here, is we're aggregating P bests instead of picking just one. And so that's the so-called, that's why this is fully informed, because you're trying to take information from everybody together. And so this is similar to consensus algorithms in some ways, where you're taking information from all of them, aggregating them together, but you are in the different methods of aggregating these things together sometimes involve using random weights on each one of these things as well. And so you might actually have, although you're trusting everyone together, you actually can apply. So, an approach here is to randomly weight P best from each neighbor. And so the idea is that you are going to take information from all, but maybe each individual takes a different combination of information from its neighborhood as someone else from a different neighborhood. So it still provides for exploration and exploitation, but it hopefully keeps them more tightly coupled together, so that the flock is kind of constantly sort of trying to stay centered while they're also exploring and exploiting. And so this is sort of this idea behind a fully integrated particle swarm. Was the hope is that this had more potential to find global optima quicker and get out of local traps. The downside is that it ended up being very sensitive to network topology. And it was never quite clear what was the best network. And so you could say best network. And so it might be true that you have one network that works really well for one objective function, but there's another network that worked well for a different, because all of this information was constantly pouring in from everyone in the neighborhood. Exactly how you were connected to everyone in the neighborhood made a very big difference. And so this fully integrated idea never quite picked up enough inertia, or I guess I'd say the inertia of PSO was sort of too much for any advantage from the fully integrated particle swarm to attract people's attention away from PSO. So PSO in itself was sort of successful enough. This is why we kind of continue to see PSO, but don't see these alternatives like the fully integrated particle swarm. So instead, we see things like shuffled frog leaping algorithm, which is sort of fundamentally different, which is the reason why it's kind of carving out a niche for itself. Whereas things that look just like particle swarm optimization fail to replace particle swarm optimization because PSO has been pretty darn successful by itself. So, so apologies for this sum here, but I'm just kind of getting the basic idea that you could rebuild PSO based on different ways that you connect information together, but you probably won't do much better than a normal PSO, and that's kind of what even the authors themselves found when they tried to introduce FIPS. How is the topology affecting FIPS? We're only calculating average p-best without looking at topology. Well, the neighborhood is defined by the topology. And so in FIPS, I could have groups that are connected on a ring. I could have them fully connected. I could have them in funny clusters. And I can then define every agent. You can define a different neighborhood around every agent, and that neighborhood would be a subset of this large graph that connects all the neighborhoods together. And so you can experiment with FIPS across a wide range of topologies and get a wide range of performances. I mean, to put it another way, FIPS can kind of degenerate into the old school PSO if you put FIPS on a ring, because now you don't actually have a lot of diversity inside your network, and so you may as well just be taking one p-best. That's kind of the idea there. Though as you scale FIPS up, where now you're kind of fully connected, then you've got a bunch of these p-bests walking around, and so it just gets a lot more complicated. So you probably won't see FIPS in any optimization package. You probably won't have a need to use FIPS, but you could imagine different ways of adjusting the ways in which things move around, kind of FIPS-like, but still you probably have a hard time beating PSO, which probably means that in the end, if you try to publish a paper with a PSO alternative and compare to PSO, you might have only marginal differences in performance, and so PSO will continue to dominate. It's kind of all I was just trying to say there. But another reason why I wanted to introduce FIPS is it kind of allows us to then pivot on what I would like to take the class in next, which are these. So FIPS comes closer to a consensus algorithm. And by consensus algorithm, I mean that you have a bunch of agents that are on a graph connected to each other, and they each have their own individual independent in opinions, and over time they share opinions with each other, and then hopefully, if things are designed correctly, converge to a single opinion. And depending on what school of thought you come from, if you're from a computer science community, then typically the opinion that they converge on is one that one of them had initially. And so you're just sort of deciding upon which opinion everyone is going to settle down on. That's kind of like genetic drift. If you have purely genetic drift in a population, then you get one strategy and no mutation, no selection, then you get one strategy that ends up dominating, and everyone has it. And so that they've come to consensus on that. From the more kind of electrical engineering side of things, when you talk about consensus, then you just care about everyone coming to one value. And that value might be a value that none of them had to begin with. So it might be the average value. And so that is kind of more like what we're talking about here, is that if they all start with disparate opinions, then they converge to a single opinion, and that single opinion might be the centroid of all of them together. And so that's kind of like what FIPS was motivated by. Is the opinion distribution discrete or continuous? So in most of these opinion dynamics cases, this is the field. then usually we think of continuous opinions. So you can think of each agent having an opinion, say from 0 to 1, but you certainly could imagine things being much more like the computer science case where everyone has a discrete opinion. So this is, FIPS was this example where everyone's contributing and potentially they all could come to agreement on what's globally best and all kind of converge there. And so we can imagine, well, let's get rid of the notion of best. And so now we just want them to converge somewhere. We don't care whether it's best or not. So in opinion dynamics, this is in some ways not an optimization problem. The problem is it's a calculation problem. Is that how do we collectively reach agreement on a value that depends on initial values? And what's nice about getting rid of the optimization approach for now is we actually have the ability to use mathematical tools that, say from linear algebra to analyze these problems. And so the problem with optimization is that we don't know what optimization function we're operating on. And so it's very difficult for us to make claims from a meta-heuristic point of view that we will definitely reach a global optimum, because all we know is maybe some basic features of the optimization criteria that we're trying to optimize over. The function maybe is convex, or the function is smooth, and so on and so forth. But in these kind of opinion dynamics problems, we say we actually don't know what there is no value to any particular opinion, but we know that every agent has an opinion. And we want to do a collective computation where we decide kind of what is the central opinion of the whole group, and how do we get everyone to converge on this idea of a central opinion. And so that, so this is where we're going to kind of move. And so we're going to introduce things like gossip algorithms, where basically we end up defining communication topologies which define how agents can share information. And then we define behaviors that happen when they receive information. And so in the case of a gossip algorithm, then for example, you might have that at every time step, agent I and its neighbor replace their opinion with the average of their two opinions. And so the beauty of this is if you combine these two things together, then very often you can do things like write, linear update rules that we can analyze mathematically. And that's kind of where I want to go with this. And that will allow us to talk a little bit more about parallel processing in general, and what goes into saying that we have a group of agents that are operating on a network together, and how do we parallelize tasks along them. And if we view these opinion dynamics as one subset of those, that allows us to kind of talk about things like consensus and converging on a common opinion as a distributed problem, and all of the components necessary to guarantee that in asynchronous time, these agents that are sharing in maybe a very socially inspired way are going to come to consensus to some useful outcome. And so we might also see things like the Nash equilibria come back up together, because coming up with a single point that everyone agrees is best for everyone, given that no one else moves, is actually somewhat like coming to consensus. And so we'll try to talk about those connections as well. So that's kind of where we're going. And again, I'm trying to pivot off of this idea that we've gone from searching a giant optimization space with a genetic algorithm to focusing on flocking algorithms, which try to stay together as they move throughout the optimization space, to actually getting rid of the optimization problem and just focus on staying together. And so how do you get agents to stay together in somehow a useful way? And we're going to sort of make, these are going to be much more kind of socially inspired than biologically inspired or physically inspired. And then after we get done with all of this, then we're going to start talking about things like cellular automata and neural networks, and then stochastic robotics, and that'll kind of round out the course. So with that, I want to sort of stop there today. Are there any questions about any of the swarm intelligence stuff or particle swarm optimization from today, or how we are moving forward? I know there might be assignment questions. You guys just finished that last homework. I'm working on getting the next assignments out to you, and I will make sure that I have generous due dates. And if things take a little too long to get out to you, then we'll maybe skip them or make them optional and so on. So I am aware of those things. Just got a backlog to work through as I'm churning online content for all my different courses. Likewise, that's the midterm again. It's the online one, and I'm still working on finishing that one up. And again, you'll have generous time. Once I release it, you'll have at least a week and a half to decide when you want to do it. And then when you want to do it, then you'll just start it. You do it all online and on your own pace, but you'll be a time limit. I still haven't finished all of those questions, and just trying to get ahead of churning all of the material that I had for in-person to online. It's just taken a little longer than I was hoping. Any other questions? All right. All right, so we're at 4:20. So I do have office hours today on Monday. So at 4:30, I'm going to switch to my office hours room, which you can find on the main Canvas page if you want to come to those office hours. So I probably will pop off this room for a few minutes and then come back at 4:30 in the office hours room. Oh, I do have a question. Somebody says, so it's 4:20. So if you want to pop off yourself, that's okay. You can feel free to leave the room. Otherwise, I'm just going to answer any last questions, and then I'll switch to the office hours room by 4:30 and probably have a couple minutes in between. So there's a question here about ACO and moving from discrete search space to continuous. I understand how the probability distributions will be updated. I don't understand the probability distributions, because in discrete space, we spray pheromone on a point. What do we do in continuous space? And so in the continuous case, basically instead of laying down pheromone on discrete options, you lay down pheromone in on the continuous group of, so if you've got a decision variable that varies from 0 to 5, then if you took a particular decision vector that for that variable was 3.3, then you will reinforce 3.3. And so so you'll put down a little bit more probability density in that, right at that level of 3.3, or maybe according to some kernel. So you can actually imagine putting a little kernel of pheromone that is mainly centered at 3.3, but might be a little bit, have a side lobe that'll go out, back and forth. And then as everyone adds to that, if every new ant is going to look at the continuous group from 0 to 5, and they are going to see these bumps that get formed by all of this pheromone that's been laid down over continuous space. So that's what we're doing, is that instead of laying them down on discrete options, we're laying them down on continuous options. But basically, we're just generating a social probability density function instead of a social probability mass function. Does that make sense, or they're still okay? I still can't see the numerator mathematically in the denominator. So, um, so I mean, all that I'm basically saying is that in continuous space, if you have a decision variable like x that is defined, again from 0 to 5, then we can imagine it has some PDF x that maybe initially is uniform from 0 to 5. And so we can imagine that this is going to have 1/5 will be the uniform density, so that the area underneath the curve is equal to 1. And so if you would like to, you just happen to draw 3.3 here, then the idea here is that you model in your algorithm as there being a 1/5 pheromone laid down everywhere. And you then, if for this 3.3, you could imagine adding to this an additional pulse of pheromone around this 3.3 so that it distorts the probability density function. And then you may need to then renormalize this probability density function so that instead of looking like that, it might now look like this, so that the area underneath here still adds up to 1. But yeah, that's the idea. In order for it to be a probability density function, the area underneath the curve has to still add to 1. So it is a little tricky, but you can basically view it as everyone is reshaping the curve, but then the instant the ant needs to draw a new realization, then that drawing function will renormalize the curve as necessary to make it back into a probability function. All right, any other questions that like to be shared with the group? Okay. All right, in that case, I will, I'm gonna stop the recording here and leave the room here. And then, oh, do we have a resource we can study about this? I've posted, I think a number of different resources on swarm intelligence on the Canvas site. I'll try to add a few more. Some of them I think do speak about ant colony optimization. In fact, I think I've posted some of the original ant colony optimization papers. I think I posted one of a paper discussing an option for continuous ant colony optimization. I'm looking at it right now, or looking over what I've posted. And if I don't, then I can see if I can add one. So I don't see one right at the moment, but I can definitely add one. There's several different implementations of continuous ACOs out there. And so I will try to add one of those to the Canvas page to have that immediately available. All right. Anything else before I close the room? Okay. In that case, see you all Wednesday.